Welcome to this session on vector-based RAG embedding. We'll explore how to leverage Retrieval Augmented Generation, in short, RAG, to improve large language model response and ground the results with your organizational content. Our session will follow these four aspects. First, we'll provide an overview of what vector-based Retrieval Augmented Generation is, its components, and the key benefits of this technique. Second, we'll cover the essential prerequisites you will need to have in place, both commercial and technical, before implementing a vector-based RAG approach in your generative AI scenarios. Third, we'll explore the key choices that you may make to improve or streamline your implementation, i.e., choice of model, chunking strategy, etc. Fourth, we'll dive into the implementation, details across different programming models, providing you with some examples and resources for Python, JavaScript or TypeScript, CAP applications, and Java. Large language models are typically trained on a large, publicly available dataset. This makes them powerful when put to general context. However, their response is not grounded on the specific context. For example, your organizational policies, procedures, etc. Training an LLM is an expensive activity. Thus, Retrieval Augmented Generation provides an easier way to bring your organizational context to LLM responses. In this technique, there are three important steps. First step is retrieval. This step is to identify and fetch the relevant documents or information chunks from the knowledge base that we are referring. This knowledge base could be a document, or, in general, a vector database, storing large sets of documents or information in the form of vector embeddings. Second step is augment. This step is to provide the document or information chunks to the LLM model. All the modern LLM models provide an option to provide additional context, which helps LLMs to understand the context better, as well as ground the response based upon this augmented context. The third step is to generate. In this step, LLM model generates the desired response based upon the prompt provided by you while using the augmented context. RAG technique helps LLMs to provide more accurate and contextually relevant answers based upon a knowledge base. Use of vector embeddings allows faster search capabilities, which enables scalable, low-latency generation. Why should you use a vector-based RAG technique in your generative AI scenarios? Well, there are three main benefits. First one is semantic search and understanding. RAG leverages vector embeddings for content representation, which captures the meaning of the text rather than just the keywords, thus semantically understanding the content. Second is improved retrieval quality because vector embedding has good semantic understanding. Retrieved results are of a higher quality and relevance to the query asked by the user. Third is scalability and efficiency. These embeddings are stored in vector databases, which are optimized for faster similarity search. This enables quicker search response and scalable generative AI applications. Even though knowledge base is large, these advantages encourage developers to leverage RAG in generative AI pipelines. The vector embedding approach is very useful in various scenarios. Semantic search and retrieval. Leverage vector embeddings to enhance semantic search capabilities, enabling users to find relevant information quickly. Contextual analysis. Use vector embeddings for contextual analysis, allowing for a deeper understanding of relationships between different data points within the database. Informed decision-making utilizes vector embeddings to build intelligent data applications, unlocking insights and facilitating more informed decision-making. Optimized large language models, LLMs, enhance the output of LLMs by utilizing vector embeddings, to optimize and add context to the generated content. To have a better understanding of RAG, it would be beneficial to understand some of the concepts. Vector embeddings are the numerical representation of text or image into a highly dimensional space, and they are generated by embedding models. While generating these embedding vectors, models preserve semantic similarity. Similarity measures are functions which evaluate the similarity score between different vectors. This assesses the semantic difference between vectors. Some of the common similarity measures are L2 distance, cosine similarity. Embedding vectors are typically stored in vector databases. SAP HANA provides capability to store and an engine to process those vectors. Real_vector is the data type in HANA which supports creation of vector serialization and performs similarity searches using chunking. In RAG, it's an important aspect and is the process of splitting large text in smaller segments, also known as chunks. We will cover more detail on chunking strategies in upcoming slides. Data flow has two main parts. The first part is embedding creation. In this step, the knowledge base, for example, text documents, PDFs, or images, audio, or anything else, is divided into small size, which are called chunks. There are several chunking strategies which may be experimented and employed. These chunks are then further converted into embeddings using a suitable embedding model. These embedding models create fixed-size vectors of the chunks, which are stored into vector engine of your choice. SAP also provides vector engine capability natively in its own SAP HANA database. Second part is querying. In this step, when a user asks a question, this question is converted into vector embedding, and then a similarity search is performed in the vector database for finding the matches. Best matches are then added to large language model prompts as augmented context, and the LLMs then generate the relevant responses for the user query. This augmented context helps LLMs to use the knowledge beyond their own training datasets before implementing. Let's cover the prerequisites needed on SAP Business Technology Platform. You'll need an SAP AI Core service with the extended tier on SAP BTP to enable generative AI hub access, SAP HANA Cloud for your vector database, and SAP AI Launchpad to configure models within Generative AI Hub. Pricing information on all these services are available in the linked resources to provide more context around these prerequisites. SAP BTP is an integrated suite of cloud services, databases, AI, and development tools that enable businesses to build, extend, and integrate SAP and non-SAP applications efficiently. SAP HANA Cloud is a database as a service that enables in-memory query processing and provides a one-stop solution with in-database capabilities for relational, graph, spatial, vector, and semi-structured data usage along with embedded machine learning algorithms. SAP AI Core is a managed AI runtime that enables scalable execution of AI models and pipelines, integrating seamlessly with SAP applications and data on SAP BTP. It supports full lifecycle management of your AI scenarios. SAP AI Launchpad is a multi-tenant software-as-a-service application which helps customers to manage their AI use cases and associated lifecycle across multiple different AI runtimes. By setting up these prerequisites, you'll establish a strong foundation for implementing AI projects sufficiently and at scale. Let's examine the high-level reference architecture for implementing our RAG-based applications on SAP BTP. This diagram shows the complete flow from end user to foundation models. Starting from the left, an end user accesses a software as a service after successfully authentication from Auth and Trust IaaS. This software as a service is hosted in BTP runtime for embedding model access. Applications leverage Generative AI Hub, which is the central component of this architecture. Generative AI Hub provides capabilities and toolset to build and manage AI workloads with dedicated foundational model access for LLM access. These LLMs are hosted by SAP or by our partners under enterprise agreements. In this scenario, the BTP application also accesses the vector engine of SAP HANA Cloud, which acts as an embedding store and providing database capabilities for indexing and pre-formatting similarity searches. This architecture ensures secure, controlled, and efficient access to AI capabilities while maintaining integration with the broader SAP ecosystem. Now, let's discuss some key decisions that impact the quality and performance of vector embeddings. Choosing the right embedding model is a key decision that impacts performance and quality of embedding. There are several embedding models which are available in open sources or from different vendors, which you may choose based upon your application requirements. For example, if you are having general-purpose RAG applications, you may choose high-performing general models like OpenAI or Cohere. Or if your application is domain-specific, there are domain-specific embedding models, which may be a better choice for you. While you may host any open-source embedding model or use an API from their vendors, SAP Generative AI Hub provides enterprise-grade access to a series of embedding models, which is a recommended choice to ensure data security and enterprise controls. Another important choice is the chunking strategy. This is how you'll break your document into smaller units for embedding creation. You may use semantic chunking, for example, sentence-based or paragraph-based, rather than fixed-length chunks or arbitrary splits. Another approach is to opt the overlapping chunks by maintaining sliding windows. This helps in maintaining the context better. Adding metadata to the chunks enables you to perform post-filtering. If you further restrict results from retrieval steps, it is usually preferred to pre-process the input text before inputting it into the embedding model. These pre-processing steps may include removing any HTML tags or document tags, excessive white spaces, special characters, etc., while you remove some of the information from the document. Keep a balance to avoid stripping any useful contextual information. Performance is very important when dealing with large knowledge bases or a number of user queries are high. Vector indexes come to the rescue as they accelerate query time significantly. You need to ensure that vector column and index hierarchical navigatable small window, or HNSW index, is one of the best options, which is also the one that's available in SAP HANA. Retrieval results are as good as content representation in the embedding. Thus, you should always evaluate the quality of the embedding representation. You can test the embedding for nearest neighbor search or use similarity scoring tools for visualization. Also run pilot queries and get the user feedback early in your pipeline development. Knowledge bases will add more documents or update the existing content, which means that in order to provide up-to-date results, embedding also needs to be updated regularly. One of the ways is the re-enabling embedding in your pipeline so that it can be executed periodically or when a change is identified. You can leverage versions for change tracking, and you may also want to store old embeddings for A/B testing. Organizations working in multiple countries most likely need to have their content and users using different languages. Thus, it is important to leverage multilingual embedding models when creating chunks from multiple knowledge sources. It is preferred to keep all the chunks in a single language. These key choices and guidelines will help you achieve better results in embedding creation of your content. Now let's discuss implementation guidelines for selecting your programming model. For backend applications, we recommend using Python, which has a very well-maintained SDK and a very robust ecosystem, or using JavaScript/TypeScript, which offers strong asynchronous capabilities and the Node.js ecosystem. For full-stack applications, we recommend using SAP Cloud Application Programming Model, which is optimized for SAP integration, providing scalability, built-in best practices, and a seamless connection with SAP services. For working in Java-based enterprise environments, there is the Java SDK to provide solid foundation for AI model interactions. While these are general best practice guidelines, the final choice should align with your team's expertise and project requirements. Now let's explore the specific implementation options for each programming model. We've broken down the resources by language and programming model: Python, JavaScript/TypeScript, SAP CAP applications, and Java. For Python developers, we recommend using the SAP Generative AI Hub SDK for building your applications. This SDK is specifically designed for leveraging generative AI models available in the AI Hub. Additionally, the SAP AI Core SDK and AI API Client SDK are valuable for managing the AI Core lifecycle. HANA_ML library exposes native AI and machine learning capabilities in SAP HANA. For reference code, we provide you with an exact code sample, but you can also check the other reference examples for JavaScript and TypeScript developers. The SAP Cloud SDK for AI is the official SDK for use for reference code. We provide you with an exact code sample, but you can also check the excellent reference code in the SDK examples, specifically looking at the orchestration file, which shows how to perform chat completions. If you're building a CAP application, we recommend using the SAP Cloud SDK for AI through the CAP LLM plugin. This also provides valuable examples. The reference code is similar to the JavaScript/TypeScript ones. We provide you with an exact code sample, but you may also check the SDK examples focusing on the orchestration file. For Java developers, the SAP Cloud SDK for AI for Java is available. We provide you with an exact code sample, but you can also check the sample Spring app example, which includes both service and controller file implementations. For each programming model or language, we provide the recommended learning journeys that walk you through the implementation process. All these resources are linked, and we encourage you to explore them based upon your preferred programming model. Each option is fully supported within the SAP ecosystem, providing secure and efficient access to generative AI models while maintaining the flexibility to choose the approach that best suits your team's skills and project requirements. Now let's look at an example of how to create vector embeddings in SAP HANA database. Consider that your knowledge source is a text file named aicore.txt. First, we will load this file, and then we'll split the text content within fixed length chunks. You may use chunk size to limit the chunk size, and chunk overlap to provide overlap among the chunks. In this example, we are using an embedding model. Text embedding 8 is 002. However, you may use other models available from Generative AI Hub. Using Generative AI Hub SDK, we will now create instances of embedding model. To store these embeddings, we need a vector store, and for that, we will leverage SAP HANA. In SAP HANA, we will use the table vector_table to store these embeddings. Once the database instance is created with the associated table, we will clear any existing content and then add the documents to the database. Using the embedding model SDK, we'll convert all the chunks into embeddings and we'll store them in a table in a HANA vector store. This concludes our overview of RAG and embedding creation process. We've covered the benefits of using RAG, the reference architecture, the prerequisites, the implementation steps, the key decision factors, and implementation guidelines with a practical code example. This best practice guide reflects the collective expertise of AI specialists from across SAP, bringing together insights to support your journey. Thank you for watching this session. We hope the information provided helps you successfully implement advanced generative AI capabilities in your business applications. Thank you.